Hello everybody, this is Dr. Gopinath Halda from Department of Chemical Engineering, National Institute of Technology, Durgapur. I welcome you all to SWAM online course of chemical engineering disciplines. Today I would like to emphasize on adiabatic flame temperature of a fuel under chemical process principles. Let us have the different portions that today I have planned to cover. So, this is basically the outlines of this module: adiabatic flame temperature, adiabatic combustion chamber, methodology of AFT computation, influence of air or fuel mixture ratio on AFT, effect of pressure on AFT, influence of temperature on AFT, illustration of problem solving technique, how to solve the problems based on the process principles, and application area, and what is the application area where it can be applied, the knowledge of this adiabatic flame temperature where it can be applied. Now, let us define this adiabatic flame temperature. What is adiabatic flame temperature? Adiabatic flame temperature is the maximum temperature can be attained by a fuel when it is burnt in presence of oxygen or air under adiabatic condition. Adiabatic, this word is basically a Greek word, and this is derived from this word, which does necessarily mean to not to pass flow of heat or not to pass of heat from one place to another. So, here this adiabatic flame temperature is the temperature when a reaction proceeds without loss or gain of a heat, and if all the products remain together in a single mass or stream of materials. So, these products will attain a definite temperature. So, this is adiabatic flame temperature, and it has several applications in different areas, and we chemical engineer people, we must know about the significance of this adiabatic flame temperature, where it can be applied. Adiabatic combustion chamber. So, just let us have a look into this adiabatic combustion chamber. So, see, this is combustion chamber, and this is the chamber where the combustion will be taking place adiabatically. So, there will be no thermal communication between the system and surroundings, and this insulation that has been made to prevent the heat loss from this system to the surroundings and vice versa. And this fuel, so this is this fuel, the combustible fuel that has been supplied to the combustion chamber for its combustion, and air, this air is generally supplied to the combustion chamber to ensure the complete combustion, because the adiabatic flame temperature that can be maximum if the complete combustion takes place in the adiabatic combustion chamber, and this is the product, that product what you can get in a single stream, and this maximum temperature is nothing but the adiabatic flame temperature, which can be attained by this product under adiabatic conditions in presence of oxygen or air. So, this is noteworthy that this temperature of a combustion chamber becomes maximum when combustion is complete and no heat loss to the surroundings. So, this is obvious. So, if there is a loss of heat and if it is lost from this system to the surroundings, so the temperature definitely it will be hampered, the maximum temperature or this combustion temperature. So, we cannot get the accurate temperature, and when this combustion is complete, only based on that conditions we can get the accurate temperature, and if there is no heat leak in and out considering the systems and surroundings. AFT at complete combustion with theoretical amount of air. So, this adiabatic flame temperature, it may be maximum at complete combustions when this theoretical amount of air is possible to be delivered, theoretical amount of air where this is possible to be delivered in this chamber. Factor dependency of AFT. So, these are the different factors on which adiabatic flame temperature of a fuel depends greatly. Adiabatic flame temperature of a fuel depends upon the state of the reactants. This is nothing but the different state of these reacting substances what has been supplied to the combustion chamber, or the combustible gas what is to be supplied to the combustion chamber for ensuring the complete combustion, and the degree of completion of the reaction, that means this is the extent of reaction, how much it can be taking place in a combustion chamber, and last one the amount of air used. So, this is very important thing, because the to ensure the complete combustion of this combustible fuel, certain amount of excess air is sometimes required to be supplied to the combustion chamber. So, this amount of air, how much this is to be supplied. So, that is also very important thing to be taken into account. Thermodynamics behind AFT estimations. So, we are very much concerned with this AFT, adiabatic flame temperature. Now, we should know how to calculate this, how to estimate this adiabatic flame temperature. Now, this is very interesting that so it has a strong thermodynamic background by which you can calculate the adiabatic flame temperature of a fuel. So, we know this first law of thermodynamics. So, this is the differential form of the first law of thermodynamics in closed system, dq equals to du plus dw. And in case of adiabatic flame temperature, since it is adiabatic, so there will be no thermal communication between the system and surrounding. So, dq is 0, and for constant volume process it will be dw equals to pdv equals to 0. So, this adiabatic flame temperature, it can be determined based on the two different conditions, constant pressure and constant volume process. So, adiabatic conditions, I mean these adiabatic combustion can be taken place based on these two different conditions. Now, let us consider these two different conditions. For unsteady state process, so there will be no change in kinetic energy, and delta U to be estimated from this delta H minus delta PV, because the total energy of a system, if it is referred to that, this change in kinetic energy plus change in potential energy plus the internal energy. So, this internal energy, so that can be computed from the knowledge of this definition of this enthalpy, delta H equals to delta U plus P delta V. So, here this for constant pressure process in a closed systems, it would be delta P V equals to P delta V, since the pressure is constant. Here it is frequently negligible. So, this P delta V or V delta P, if these are treated as the negligible amount for these two different processes, then basically what we are getting as a resulting equations is delta H reacting substances equals to delta H products. So, this is the concept where this calorimetrically that we can find out the adiabatic flame temperature, where this H or Q is nothing but this mCpT. Now, this heat balance towards AFT estimations. So, this is the basic heat balance equation what we can consider for the AFT estimations. This is done to calculate the AFT, where the sensible heat in air plus fuel, heat of combustion, heat absorbed due to dissociation of products of combustion, sensible heat in product of combustion, heat losses from flame to the surroundings. That means, this is a very simple system where the fuel that is supplied, and to ensure the complete combustion, the excess amount of air that is required to be supplied for complete combustion, where we will be getting on completion of this reaction, we will be getting the products in a single stream, and these heat balance that is to be done in the same fashion what we can consider here, considering the sensible heat and the heat losses from the system also, because the system what we can devise in real practice, that is not always possible to be fabricated where we can get the 100% leak proof system. So, there might be a slim chances of heat loss. So, that is to be also taken into account. So, these are the different assumptions that you can consider for the calculation of this AFT, where this combustion is adiabatic, since it is adiabatic flame temperature. So, where this combustion that is to be necessarily adiabatic, and complete combustion occurs and produces carbon dioxide, sulfur dioxide and steam. Dissociation of products of combustion is neglected. So, this dissociation that might be happened due to the high temperature, high pressure. So, that might be neglected, and combustion takes place at constant pressure mostly. So, that this delta H equals to delta Cp dt. Now, these are the different steps that we can calculate, that you can consider basically for the AFT calculations, where the entropy changes for the reactants from T1 to 298 by delta H1, the enthalpy changes for the products from 298 to T, and the adiabatic flame temperature by delta H2. So, this is the basic equation what we can consider, this delta H2 equals to minus delta H1 minus delta H superscript 0 to 98. So, this is nothing but the term for the standard conditions, I mean for 1 atmosphere and 25 degree centigrade, and basically this delta H2 and delta H1, these are concerned with the products and the reacting substances, and that is to be considered here. To determine the maximum attainable temperature, so this summation of Hp equals to summation of Ani 298 to T Cpi dt plus this summation of Ani alpha. This is basically the special case where this latent heat of vaporization that we can consider. Basically, the phase change processes that are associated, like vaporization, this sublimation. So, these are the different process, and here the equation, this equation that I have already told. So, this is delta H2 equals to minus delta H1 minus delta H2 98. This is the basic equation that is to be considered here for calculating this adiabatic flame temperature. And these equation, this summation of Hp equals to ai T minus 298 plus Bi by 2 T square minus 298 square plus Ci by 3 T to the power 3 minus 298 by T to the 3 plus summation of A and I lambda I. Actually, this equation, this Cp in terms of power series, basically this equation will be considering when this Cp varies with respect to the temperature. I mean, Cp not necessarily to be assumed as constant value, this is changing, this is varying with respect to the temperature variation. So, this Cp when it will be varying temperature on this temperature, I mean the subject to the temperature variation, Cp also will go on varying. So, that variation in temperature which in turn changes this Cp. So, that will be considered also. So, here if the heat of formation of reactant and products given, so then find delta H reaction, that means the heat of reaction that is to be considered. Sometimes it is given in the problem that the heat of products and the heat of reacting substances. Okay. So, these are the these are the enthalpy changes that is to be considered to get the enthalpy of these reactions. Now, effect of temperature on AFT. So, let us have a look into this graph where this adiabatic temperature versus this temperature at which this combustion will be taking place, where just see this is the findings where this is observed very clearly that just AFT increases with increasing temperature, and this increment, that means this temperature when it will be going on increasing, the AFT that will go on increasing also. So, this AFT when it increases, so where there may not be the change beyond this 3000 Kelvin. So, beyond 3000 Kelvin most of the liberated energy goes into the dissociating the stable species. So, this is very common observation that this AFT normally increases with increase in temperature. So, this is nothing but the influence of temperature on AFT. Similarly, we can consider the effect of pressure on AFT, where this AFT increases with increase in pressure. At high pressure, dissociation of stable molecules decrease, because this pressure when it will go on increasing, when it will be high. So, in that case there is a chance of dissociations of these stable molecules participated in the reactions. So, increase in AFT is limited beyond 0.8 MPa. So, that is also basically observable from this figure. So, it is due to negligible or no change in chemical composition at high pressure. That means, there is no chance of changing chemical composition at high pressure. So, that is why here this beyond this pressure. So, this is very negligible. Effect of equivalent ratio on AFT. So, equivalent ratio, this is nothing but the fuel air ratio or this mixture basically. So, this is expressed here, this phi equals to 1.05. AFT increases with increase in equivalence ratio. It means that it does necessarily mean that when it increases, the AFT that increases also. Beyond this value, I mean phi equals to 1.05, flame temperature decreases with equivalence ratio. With increase in inlet temperature from 300 to 600 Kelvin, the curve is shifted upwards, and that is very clearly observable. So, this is that can be seen from this graphical representation, that nature of this curve, and when this is going to be shifted for the change in temperature. Illustration on AFT estimation method. So, this is nothing but an problem. So, where we can consider this carbon dioxide, if it is a gas and if it is supplied to the adiabatic combustion chamber with 100% excess air, when the reactants enter at 100 degree centigrade and 1 atmosphere, and these are the heat capacities value that are given and that are assumed to be constant. So, in that case standard heat of combustion this is given. So, we need to calculate the theoretical flame temperature for this carbon monoxide. So, let us have a look what is the procedure, what are the different steps to be taken into consideration for the calculation of this adiabatic flame temperature. So, first of all let us have a basis for what we can go ahead for the calculations. So, 1 mole of carbon monoxide at 25 degrees centigrade, that has been opted as the basis of these problems. Now, this reaction involved is carbon monoxide is oxidized to form carbon dioxide, and it has been schematically presented here, this reactor at which temperature this is entering, air, this is at which temperature this is entering, and what are the products, possible products that we can have in a single mass, a single stream in the product outlet, and then the maximum temperature can be attained by this fuel under adiabatic condition when it is burnt in presence of oxygen and air. So, this is the component for entering reactants, where this carbon monoxide 1 mole, oxygen required is 0.5 mole, that we are getting basically from the stoichiometric equation, and oxygen excess, that means based on this 100% excess air supplied to ensure the complete combustion in a combustion chamber. So, we are getting 0.5 mole. So, that 0.5 mole if we can add, so then total oxygen that will be getting 1 mole, and nitrogen this is 3.776, that is the inert gas that is present in the air, and here this 79 by 21 we are getting 3.76 mole, and that will remain present also in the product stream also. So, here this you see these exit products, where these components definitely carbon dioxide that you are getting from these chemical reactions, carbon dioxide will be the product, and oxygen that will be also there, and nitrogen that will be also there, because nitrogen is inert, and oxygen, the excess amount of oxygen that will also be present in the product stream. So, for entering string and for leaving strings, where this delta H1, I mean the enthalpy changes that you have considered, and this delta H2, so these enthalpy changes that you have considered, and the constant average heat capacities are given for these different reacting substances in the product that are considered here. So, calorimetrically these equations we have considered for finding out these enthalpy changes, and finally the adiabatic flame temperature. So, this is the temperature that you can get, and here this temperature is 1820.1 K. So, this is the way by which you can calculate the other for other problem we can calculate the adiabatic flame temperature. So, here this theoretical flame temperature of a gas having 20% CO and 80% nitrogen, this is a similar kind of problem, only the basic difference is here this 150% of excess air has been supplied, and the main stream as compared to the earlier problem where this carbon dioxide and nitrogen. So, basically this is a mixture, so that we need to consider, and here these heat capacities are given that are assumed to be constant, and this heat of formation at 25 degrees C that are given. So, this is to be considered for finally finding out this adiabatic flame temperature. So, these are the hints that we can give here for better understanding and to proceed for the calculations of these AFT. Problem solving technique. So, here one more problem, this is little bit different in nature, where one thing is, so this dry methane that has been considered as one of the combustible gas has been supplied to the system, I mean the adiabatic combustion chamber, and the 100% excess air has been supplied to ensure the complete combustion of this methane, where this heat of reaction is minus 802 kilojoule per gram mole of methane. So, that is the standard heat of reaction. Now, here 20% of the heat produced is lost to the surroundings, because that might be happened because if there is a leakage in the adiabatic combustion chamber. So, it can happen, it can be happen, basically this heat produced. So, that is lost to the surroundings from this system. So, how this is to be taken into consideration for finding out this adiabatic flame temperature? The procedure as I have already told. So, this is basically same, this basis what you have considered here, that is to be opted here, and this chemical reaction involved, the methane is oxidized to form carbon dioxide and water, and similarly we can split it up for these entering reactants and the exit products, where these components are gram mole. From the stoichiometric equation what you are getting, this methane 1 mole, oxygen required this is 2 mole, oxygen excess is 2 mole, because 100% excess air that has been supplied, and the total oxygen is 4 and nitrogen is 15.05, that is basically getting from this the standard ratio, I mean 79 by 21 into 4, and the exit products, these components and gram mole. So, these are the exit products, because this nitrogen that will be present in product stream also, and carbon dioxide, water. So, that we are getting from the stoichiometric equation, and oxygen excess air it contains this oxygen, and that will remain present in also in the product stream. So, this heat given out. So, this is the tricky point where this given out heat is 802 kilojoule, and heat loss, how much the heat loss is, let us calculate this, how much the heat is lost from the system, and then this is to be subtracted from the total heat of reaction. So, finally, after subtracting we are getting 641.6 kilojoule. So, that is to be considered as the final temperature, where this is to be equated to get the value of this T, I mean the adiabatic flame temperature. Otherwise, the process is same, the specific heat values. So, these are the values, this is basically the Cp variation with respect to the temperature. I mean when this Cp will go on varying subject to the temperature change, so definitely the adiabatic flame temperature. So, that will be calculated based on this Cp variation, and here how to handle with this Cp variation with respect to this temperature, and where these equations, I mean the equations in power series in terms of this A plus Bt plus Ct square plus dTq. So, this equation how it is to be considered. So, average specific heat values. So, in the last slide what you have seen, this carbon dioxide, carbon monoxide, H2O, N2, H2, where this equation that you have considered for the Cp values. So, here, so it is little bit complicated and it little bit tough to consider in the problem for finding out this value of T. So, if we can take it as average specific values for this carbon dioxide, then in that case what we can consider, and this is the average value that has been finally considered for getting this AFT. So, this is the equation, these are the different equations that you can consider to express the Cp variation with respect to temperature for the different I mean the reacting substances and the products. Here this CO and nitrogen, so this is basically the mixture where this ratio that is to be considered, but only the thing is where this carbon dioxide, oxygen and nitrogen, where the Cp is not necessarily assumed to be constant, this is varying with respect to the temperature, and that has been given. So, here this is to be considered, and the chemical reaction as usual what you have considered, this is the equations that will be considering the basis that you have chosen 1 gram mole of CO, and entering reactants carbon monoxide, this is 1 gram mole, oxygen supplied this 0.5 multiplied by 2, this is 1 gram mole, nitrogen in feed, this is 1 gram mole, nitrogen from air, this is 3.76. So, total nitrogen this is 7.76 gram mole. Combustion product. So, what we are getting from these chemical reactions, so where carbon dioxide is one of the products and oxygen, the excess oxygen how much it is, and that will remain present also in the product streams, and nitrogen since it is inert, so it will also be present in product stream. So, this 7.76 gram mole, the intact amount that will remain present since being an inert gas. Now, enthalpy of these products as you have already considered. So, here this is little difficult in appearing, but if we can take this average specific heat as you have already discussed in the last, I mean just to the last to last slides, where if we can take this average specific heat. So, we can get this equation in little simplified form, and we can feel comfortable to calculate this AFT. So, this is the value that you have got here, and AFT of fuels at stoichiometric mixture. So, this is very important thing. So, this is very interesting that these systems where this methane air, I mean the combustible gas that is supplied to the combustion chamber, and to ensure the complete combustion this air is supplied in the combustion chamber. So, where the methane if it is combustible gas, and in that case you let us have a look onto this figure. You see this hydrocarbon air, and these are the different temperatures, this 300, 300, 600. When temperature increases, then this AFT that also increases. So, that we are getting from this table, but this is within an appreciable range. This see this 2200, 2270, 2500, where this is for the combination hydrocarbon air. Now, when this oxygen, when this is supplied instead of air, so then you see just have a look onto this figure of this AFT where this temperature is 3030. So, this is high. Now, at this temperature 300 degree centigrade and this pressure 0.1 MPa, and here this AFT 3030, this is the adiabatic flame temperature what you are getting. Why? What is the reason? Basically, this oxygen that contains no nitrogen as it was in air, and since this nitrogen this is it will take also certain amount of heat, and this heat will be absorbed. So, this heat that is also to be taken into account. So, here oxygen in case of that, so there is no chance of that amount heat to be considered what you are considering basically from nitrogen. So, here this oxygen and methane, so these combinations where the temperature AFT, I mean the AFT will be more. Why? The subject to this excess air, so this complete combustion will take place and the temperature that will go on increasing. Similarly, for other C3H8 air, H2 air, H2O2. So, where air is there, I mean nitrogen is there, so it will be getting much amount of heat. Okay, so that is why this temperature that will also go on decreasing, and here this hydrogen oxygen, here this oxygen is there, again you see this temperature just let us say noticeable figure, this is the 3080, this is the temperature that we can have. So, we can have some knowledge about the stoichiometric mixture under certain influence of this temperature, this mixture proportion, I mean the ratio and this pressure, and what kind of adiabatic flame temperature that we can have. Application of AFT and major conclusions. This internal combustion engine nozzle. So, these adiabatic flame temperatures. So, these idea where you can apply. So, this is basically the area where this adiabatic flame temperature that we can apply, where this internal combustion engine, where this nozzle, evaluation of fuel quality, I mean whether this fuel this is suitable or not. So, that can be assessed with the help of this adiabatic flame temperature. And here higher the, and it is observed that higher AFT means higher the adiabatic flame temperature, better is the quality of this fuel. So, this is the kind of observation if we can get. So, definitely we can evaluate. Design of a thermal reactor. So, thermal reactor, we chemical engineer people, we require to consider the design of thermal reactor for chemical reaction engineering laboratory, for energy laboratory. So, where this thermal reactor, this thermal reactor necessarily consists of different layers. If we can consider just Maple furnace. So, this Maple furnace, it necessarily consists of 3 different layers. One is innermost layer, intermediate layer and outermost layer. So, these 3 different layers are made up of different materials, and basically these are serving the 3 different purposes. So, where this material, what material should be recommended by the chemical engineer and the process engineer or the furnace engineer. So, that depends on also the temperature, I mean the process, what process that will be taking place inside this, and the temperature, how much the temperature that can go up, I mean what kind of high temperature that we can have, and the materials what we can consider which can tolerate this temperature. So, this is the kind of thing what we generally do for considering this AFT. Now, these major conclusions. So, this is one of the very important conclusions that you can have. This maximum temperature encountered in a combustion chamber is always less than the theoretical adiabatic flame temperature, because combustion is usually incomplete and some of heat loss occurs, some combustion gases dissociate at high temperature. This is very obvious, definitely this is clear and understandable to all of us, because if there is a chance of heat loss from the system to the surroundings, so definitely this temperature that will be less. So, actual flame temperature and the theoretical flame temperature, it will be different. Then generally in real practice this is not possible to achieve the 100% leak proof systems. So, where there might be a chances of heat loss. So, if it is taken into account to get the temperature, then actual flame temperature will be less than the theoretical flame temperature, and the second chance is where the dissociation of these products. So, that is also in one of the reasons by which, so this temperature that may be lower. So, these are the 2 basic reasons by which you can say that this temperature, it will always be less than the theoretical temperature. So, these are the books that have been adopted here for developing this module. So, thank you very much. With this deliberation I can stop my discussion here, and I hope this information on AFT will be very productive to all the research audience and the students, and you will get an opportunity to implement its commercial applications. And so, see you in the next time. Thank you.